Greetings, Ben Pearson, the Roser Tracker. We're back with our series on studying the effects of global warming, and we're at the second of the three questions I had established previously, which is, could the rise in CO2 levels that we're seeing actually cause global warming? Now, let me say first and foremost, the math behind this is very, very complex. But it really comes down to a couple of simple principles which I have put into this calculator here that I have that will show some of these points. So we're going to go ahead and see what kinds of things that we can come up with to explain this, and we'll go from there. So the first thing that I want to tell you guys is, what is the math behind this particular website? So this is a website. I will post a link in the description below. It's a hidden site on my Where is Roadster page. It's been up there actually for a little while. But it will show what some of the basic math is. And fundamentally behind this is something called black body radiation. Now, black body radiation basically means that everything that has a temperature will radiate some kind of heat out into the universe. So the easiest thing to see this, if you have a cool stove, like an electric type of stove, and you see it slowly heat up, then you'll see it first go from completely black to a little bit of red, a kind of dull red, and then it'll become a brighter and brighter color, maybe even to a bright white color, that will show how effective it is at actually producing heat. The hotter it gets, the brighter the color becomes. And there's a couple of different laws that are in there, but they're all through the Stefan-Boltzmann law. I have a link on the website, which I will try to remember to leave in the description as well. But this particular website will show some of the formulas here, but it doesn't particularly matter. This law here, that the scales to the temperature to the fourth, is really the key thing that we're looking for. This is a fairly complicated calculator, but let me explain some of the basic things. You have some different presets that you can choose from above, and they all have some different things that we'll take a look at in a moment. The key things, though, that you can enter is the solar radiation. This is how much energy are you receiving from the sun outside of the atmosphere of whatever planet it may be. So if you have a satellite that's orbiting Earth, when it is in sunlight, it will receive 1361 watts per meter squared. You can look this up for whatever planet that you care to, but this is how bright is the sun effectively at that distance, and it falls off as the square of the distance that you get from the sun. The albedo is how much light is reflected from it, and this is a combination of the reflectivity of the surface as well as whatever clouds there may be. For instance, the surface of the Earth tends to be fairly dark, but the clouds are fairly light, so the albedo of Earth is 31%, which means that as a whole, the Earth reflects 31% of the light that we receive from the sun. It never hits the ground, never is absorbed in any way. And this will vary planet by planet, but the moon, it's going to be a little bit darker, so this number will be a little bit lower, and we'll see that in just a moment here. The last one is the normalized greenhouse effect, and this is basically how much of the heat that is radiated from the surface of the planet will actually leave the planet, how much of it is reabsorbed. So a number of 1 would be perfect absorption, and Venus is a very, very good greenhouse planet. You know, it has an extremely good greenhouse. Its normalization factor is 0.99, which is just about as high as you can realistically get. If you have no atmosphere, it's going to be 0. So we're going to start out by playing with the moon. Now, I forgot to also explain these little sliders here. This will control what you see on here. You will hold whichever one of these things constant, or you'll see what happens when it varies what the average temperature of the planet is. The units here are Kelvin. 273 Kelvin is 0 degrees Fahrenheit. Kelvin works on the absolute zero scale, so 0 is the lowest temperature you could possibly have. And 32 degrees Fahrenheit is the same as 0 degrees Celsius. So it doesn't particularly matter for this, other than to know that this is a Celsius scale. The key thing is could the amount of warming that scientists are talking about, which is warming of a couple of degrees, happen because of an increase of CO2? So what we'll have to do is assume a different normalized factor here. So we're going to start out with just the moon, and you see the albedo here is 12, pushing the moon preset. The solar radiation is the same as Earth because on average it's the same distance as the Earth is from the sun. So let's first look at what the average temperature would be if we change the brightness of the sun. Now, if you lower the brightness of the sun for the moon, then the temperature does go down. It goes down to 226 if you cut the solar radiation in half roughly that we're getting here. So this would be similar to maybe Jupiter moons or something like that, and that actually holds true. That's about how they are for something that was as dark as the moon, and that will vary quite a bit. As you go to something higher, then it'll go quite a bit higher as you get closer to the sun. Okay, that's straightforward enough. Now if we click on the albedo and have to hit calculate again, then this is how much is changed based on the reflection. As you can see, the more dark something is, the warmer it's going to tend to be, which checks out. If you have put something dark and something light in the sun, then the dark thing will tend to be a lot warmer when it's receiving direct sunlight. It'll radiate that heat out quicker when there is no sunlight, which is why the asphalt will get to be very warm to the point where it will actually melt snow during the day, but during the night its temperature will actually drop quicker than the surrounding earth, and so you'll have ice on there where you may not have ice in other locations. So the Earth's albedo was about 31. So if we had no atmosphere, the temperature of the Earth would be 253 degrees Kelvin, roughly, which is about -20. And if we click here, Earth, then you can see that the average temperature is 285, which is, about 30 degrees warmer. So we're about 30 degrees warmer than we would be because we have some kind of a greenhouse effect. So let's say that the temperature varied here, or that the greenhouse gases was varying. And you can, again, play with all of this as your heart's desire. So we can see here at the bottom, we go from a value of 0.38, which is the current rough approximation for the average temperature based off of the current CO2 levels. If you increase this factor by 1, then we go up more than an entire degree centigrade. And really, this normalization factor, you can look through in this Wikipedia article. I'm not actually going to go through there. These numbers are actually fairly reasonable. The CO2 levels have increased by about 40% roughly, and we have seen the rise in temperature to be about a degree. So that's about how much the normalized greenhouse effect has changed based off of the CO2 that has been emitted since the start of the revolution, of the Industrial Revolution. So let's take a quick peek at some of the other planets. Now, Venus, of course, is the really, really hot one. Venus receives about twice as much sunlight that hits the planet as we do, but Venus is a very, very bright planet. It reflects a lot of that back out, which actually makes quite a bit of a difference when it comes to it. And so as a result of that, then the albedo is very, very high, and it actually receives less light that hits the ground, that hits the atmosphere and heats it up than Earth does, which is actually kind of crazy if you think about it, because it is twice as bright there as it is here. But a lot of it reflects out. So why is Venus so hot? Venus is one of the hottest places in the solar system that's not actively a star or the center of a planet or something like that. And it's because of this greenhouse effect. Now, the atmosphere of Venus is much, much thicker than that of Earth's. It's about 100 times roughly. And a lot of that is carbon dioxide. It also has sulfur dioxide and some other things. And so the normalization effect that I was able to find was 0.99. And you can see the temperature is quite high. If you were able to lower this normalization factor even just a little bit, then Venus would actually become somewhat habitable. Earth type ranges are more in this range, 0.62, which just shows how much the albedo makes an effect. So Venus is dramatically warmer than Earth, but there's less sunlight that actually is absorbed there because most of it's reflected out, which is kind of amazing to me, to be honest. And we can look at some of the other things. We can look at Mars. Mars has the solar radiation, again, it's about half of what Earth's is. The normalized greenhouse effect is pretty small, though, on Mars. And we're varying that now. You can see, though, that this 0.11 makes a difference of, 6 or 7 degrees. And mostly that will keep more of the temperature in at night. But there's not really a lot of greenhouse effect on Mars to speak of. It is quite a bit darker of a planet, though, still. So the albedo is pretty low, so it's able to absorb a lot more of that light that comes in than Earth, but it still does not have nearly the amount of sunlight as Earth, so it's kind of interesting. And then the last one that's kind of interesting is Titan. Now, Titan's normalized greenhouse effect is a little bit weird. It actually has some materials that act as an anti-greenhouse that are in its atmosphere. So they will allow the heat that is coming from the moon to go back out, but they'll actually reflect out the heat. So they're kind of the opposite of a greenhouse gas, which is kind of interesting. But the solar radiation is considerably lower at just about 15 watts per meter squared. So it's 1% roughly of what we get on Earth. And the albedo is, again, fairly low, so it absorbs a lot of the light, but you can see the temperature is quite low. And everything else is either a gas giant or a airless moon that's in the solar system. So these are really the interesting things that you can play with. So how does all this check out? The key thing as far as global warming is concerned is, could we actually see that increase of the normalized greenhouse effect based off of the CO2? Now, this is somewhat tricky to really say in a really, really good manner. To really have this narrowed down, we would need to look into where the solar radiation is coming in. We'd have to look at the specific windows. And there's some interesting things here. The carbon dioxide that is the primary greenhouse gas that we're concerned about here, it's not the only greenhouse gas. Water is also a greenhouse gas. It actually absorbs most of the energy already. But what happens, it's kind of like if you stack on an extra blanket. Now, if you have one blanket, I used to live in a house that didn't have a whole lot of insulation, and there was no heating in the upstairs really in this house. And so it would get very, very cold. This was in Kansas. During the winters, it would get, quite cold a few days per year. And so we stacked on a whole bunch of blankets. Now, each blanket in and of itself is capable of absorbing the heat that's being produced. A blanket is literally a greenhouse gas type of thing. But you stack on the more blankets, and effectively, it makes it so that the energy takes longer to get through there. And so your temperature differential is less. Some of that heat comes back down, some of it goes back up. The amount will go down dramatically of each blanket. The difference between 0 blankets and 1 blanket is huge. The difference between 1 and 2 is still fairly substantial. The difference between 4 and 5 is not particularly high. But that increase in the number of blankets does make a difference, and it will help to heat everything up and to keep the heat trapped in there. And that's effectively what we've done. We already have a blanket of CO2 that does do a considerable amount of warming of the temperature, but adding in an extra blanket does help to keep just a little bit more heat trapped in there. And that little bit of extra heat that is trapped in does make a difference, and it can very well raise the temperature by a degree or two. Keep in mind, with no gases, the Earth would be heated by about 30 degrees Kelvin if we didn't have the water vapor and the carbon dioxide. Carbon dioxide is one of the major components of greenhouse gas warming, along with water vapor. The two put together do the vast majority of the heating. And as a result, when you increase the carbon dioxide, then it's like you're putting another blanket on, and yeah, it could easily raise it another degree or two. Maybe it's not that much, but you're doubling the thickness of what is out there in one of these particular layers. It's going to have an effect. And granted, we haven't hit the doubling yet, but the point still stands. The more carbon dioxide that we have in the atmosphere, the warmer you would expect the temperatures to be. And it is not at all implausible that the amount that we have seen, where we have seen the temperatures go up by a degree or two over the course of raising the amount of carbon dioxide from 280 parts per million, roughly, that we were seeing pre-industrial to the 420 or so today. So an increase of about 50%. That's entirely plausible. So the last remaining question, and we'll look more into this next time, is what would a difference of temperature actually do? And one of the key things that I could say is that the last ice age that we went through, and we know that there were some pretty dramatic effects that had happened from that, was caused by a difference of 4 degrees Celsius in temperature. So really not a lot of temperature difference, and it made a huge difference. Anyways, we're going to dive more into this, and I think this is an important subject, and I'm coming from this from being a person who's fairly skeptical of the whole thing. I have long believed that we should have some kind of energy independence. I've been a big believer in electric vehicles for a long time, not because it was an environmental thing to do, but because I didn't want to support the nations that produce the oil that we use, and most of those don't like our country very much. So I figured anything to get away from Middle East or Russian oil was probably a good thing. But that being said, the more I look into this, the more it really makes sense. And I'm not a climate scientist. I have a background in engineering, and I'm generally speaking pretty good with math, but I'm still learning quite a bit when it comes to this. Anyways, thank you guys so much for your support, for all you do. Let me know whatever questions or comments you guys have about this. I really want to know. And let's dive into these specific things and study them. And these are things that you guys can do too. If you have any more ideas, love to hear them. Thanks for everything. Until next time, keep on tracking. Take care. We'll see you then. Bye-bye.